Hi friends, today we are going to start lecture 44 on our helicopter dynamics series, and today I'm going to discuss the flap equation, and we are going to focus on the right hand side of this equation, which is about the forcing. I'm Dr. Anjan Ganguly. Now in the last few lectures we focused on helicopter performance. We looked at power and we developed various expressions for power using the BET approach. And today we are going to look at how to use the BET approach to get the right hand side of the blade flap equation. And in following lectures, I'm also going to cover the lag and torsion equations. And all these are for the vertical flight type of situation. So let's go back to the flap equation. And for simplicity, we will assume the case where there is a hinge at the root. And so this equation essentially has flap frequency of 1 per rev. So the coefficient here nu beta is simply 1. And now we turn our attention on the right hand side of the equation, which is given by this gamma m beta bar term. Now this particular m beta bar can be expressed in terms of Fc, which is the vertical force acting at a given section, which is at a distance small r from the blade root, and there is a small piece dr here. So now BET lets us calculate some expressions for Fc. So you have seen that Fc is approximately equal to lift. And so I can use the expression for lift which we have used before, and I use the fact that U is approximately equal to Ut and phi is approximately equal to Up by Ut. And with this I get this simplification here. I get the term theta Ut square minus Up Ut. Now in vertical flight, Ut is going to be rotation speed into r at the given location at which you are at. So the tangential velocity on the blade is coming completely from the rotation of the blade. Up is going to be capital V plus small v, where capital V is the climb velocity, small v is the induced velocity at the rotor disc, and this can be expressed in terms of lambda into rotation speed into blade radius. So I bring in these substitutions into the expression for Fz here. And then what I do is I keep on simplifying this expression. So I bring in lambda here in place of v plus small v, and then I take the terms out and cancel some of the terms involving rotation speed. So I get this term here, theta r cube minus lambda r square. And then I integrate this expression here. So once I integrate this expression, I basically assume that theta is constant and lambda is constant. And with those, I can get this in a simpler form. And then I can write this as theta by 8 minus lambda by 6. So that's the expression for m beta bar. And remember, I made this key simplification here that theta and lambda are constant to find this particular integral out. So my flap equation now assumes a very nice and simple form. Beta double star plus beta is gamma theta by 8 minus lambda by 6. So remember, gamma is dependent on density of air. So if density of air is 0, then this right hand side would vanish and you have the flapping blade in vacuum condition. Now in some cases theta would be a function of r, lambda would be a function of r, and in those cases you can do integration in some cases such as linear twist, which I will explain next. And also if the distribution is quite complicated, then you may have to do some kind of numerical integration technique such as trapezoidal rule or Simpson rule or Gauss quadrature. So let's take the simple case of linear twist. So we take theta is theta 0 plus r theta tw, and we substitute this into our equation for m beta bar and we expand it out. Now we keep doing the calculations here. So again theta 0, theta tw are constant, and lambda is also a constant, so I can do these particular integral calculations, and so finally we get this term here. Now if the blade had no twist, theta tw would be 0, so I would get back the expression which I had for the untwisted blade or the blade with constant theta 0. So in this case, for the flap equation with linearly twisted blade, I would get beta double star plus beta is this expression in terms of gamma, theta 0, theta tw, and lambda. So again, lambda here, of course, would come from momentum theory. So we could plug that lambda here, and theta 0 and theta tw would be known for a given blade. So that's the equation for flapping equation with linear twist. And we clearly see the right hand side is a steady forcing term, and gamma is the log number. So gamma is rho ACR4 by IB, which you can calculate for any given rotor. Now in vacuum, rho would be 0, that is the density of air is 0, and therefore there are no loads, and therefore the loads in the flap equation completely come because of the presence of air. And BET lets us calculate these particular loads. So essentially the left hand side of this equation is completely structural, or we can say dynamic, and the right hand side of this equation is completely coming from the fluid mechanics forces. And this particular system is a very simple system where you are essentially combining the dynamics with the fluid mechanics of the system. So the integrations we did here were quite easy, and we had presumed that the blade is hinged at the root. If you have a hinge at some distance from the root, which is typically the case, an offset of distance e, then again you can use the different equation and do all the calculations. The integrals are likely to be somewhat more difficult because you will have the integral going from e to r instead of 0 to r. Now that is something we have to do for the lagging blade, which we will do in the next lecture, because in the case of lag you always need E there, because without E your lag frequency may actually become 0 if you have no hinge spring. So we will see that particular issue in the next lecture, where we are going to look at the lag equation and focus on the right hand side.